be calculating will be quantities of the order of 10 to the power n, but these are so huge that physical quantities will be proportional to their logarithms. So if you calculate this quantity 10 to the power n with an error of an overall factor of n, I repeat, n is itself 10 to the power 23, so instead of obtaining 10 to the power n, you just got 10 to the power 23 times 10 to the power n. In general, you will say that that's a huge error. Well, this is n times logarithm of 10 plus logarithm of n. This is some number of the order of 40. This is some number of the order of 10 to the power 23. So this, you can just ignore it. It won't change anything. So this is nice because, in most cases we will not be able to obtain exact solutions, but we can approximate them. As long as the mistakes, the errors we introduce are just overall factors of the order of 10 to the power 23, well, we will get the correct answer. We will also carry out many summations of, let's say, an, some factors an. But an's, in general, will have such a dependence. There will be at some point, you see, an's themselves are of the order of 10 to the power n, if they are 10 to the power n in general. So this will be their, this peaked distribution will be more or less their distribution. So this sum will be approximately equal to, well, there is an 0, that is the maximum value. Let's say that there are n terms of the same order of magnitude as an 0, the maximum value. Now that's a huge number of terms. But you see, this is nothing but this is, for all purposes, it will be an 0. So there will be many often cases where we need to calculate the sum of many terms, but for all our purposes, since these are also huge numbers, numbers of the order of 10 to the power 23, this will be approximately nothing but the maximum value, the term that has the maximum value. I don't need to calculate that sum. Just find the term that has the largest value and we are done. The contributions of the other terms will not change my results. Well, such weird properties will also appear for probabilities. You see, we will be talking about probabilities. Well, in physics, except in quantum mechanics, we don't talk about probabilities. We have definite relationships, definite results. For example, even for the ideal gas, this will be a definite result. PV is equal to nKT always. But we will start with probabilities and then obtain definite results. So what will happen is our probability distributions will also have such a behavior. So there will be some, for example, if this is my probability distribution, for some number n, well, you see, in principle, n can take any value from here, from 0 to whatever the largest possible value is. But for all practical purposes, when you go and look at the value of n, you will see this number n0. Well, there will be some fluctuations around n0. And we will see that this delta n over n0, n0 is the, let's say, the average value or the most probable value, whichever one you want. Delta n is the fluctuation. This will turn out to be of the order of 1 over square root of n, or 10 to the power minus 11. You see, our measuring devices in general are not able to measure such small fluctuations. You will never see this fluctuation unless you are very, very unlucky. You see, typically, if you want to see a fluctuation that is that is larger, somewhat significant to or larger than delta n, you need to wait for longer than the age of the universe. So practically, you will not see that. Although we will be dealing with probabilities, our results will be valid with a probability 1. The probability of observation in violation of most of our results will be 0, assuming n is of the order of 10 to the power 23. Of course, if you take our results and try to apply it to systems with n is equal to just a few, you will see violations. But for realistic macroscopic systems, you will not observe any violations. A simple example. I do advise you to look at this. Just take a box, divide it into 2. And let's say that at a given moment, there are particles inside. If you just follow one particle, the probability of it being on the left-hand side, let's say, is 1 over 2. The probability of it being on the right-hand side will be 1 over 2. So this is, you just pick one particle, you follow that. And if you ask, and I tell you that the probability of observing it on the left half is 1 over 2, the probability of observing it on the right half will be 1 over 2. Then you can calculate the probability that n particles are on the left. Let me write PLN. What is the probability that I have small n number of particles on the left? So what will this probability be? Times. You see, saying that n of these particles are on the left also tells me that, let's say, the total number is n, the remaining ones are on the right. So I have to also multiply with that one. And in fact, if we just sum over all n from 0 up to capital N, with this factor, it is just 1 over 2 plus 1 minus 1 over 2 to the power n. This is 1. And without that, it's not even properly normalized. But you see, if you plot PL of n, n is the total number of particles, that probability distribution, even for capital N is equal to something like 100, this is for 1 over 2. And you can actually plot this in whatever computer program you are using to do your analysis. This will be the picture. So what this tells me, well, if I look at it at any moment, at a randomly selected moment, half of the particles will be on the left, half of them will be on the right. Of course, there can be one more than half or one less than half at a given moment. But if you have capital M particles, which are 10 to the power 23, just having, I don't know, 10 to 10 more particles on the left than on the right, you won't be able to differentiate it anyway. So although we are looking at a completely probabilistic system, if you ask me what is the number of particles on the left, I will tell you that it is capital N over 2, definitely, and your measurements will confirm me. So again, although we are talking about probabilities, the results we obtain will be definite.
For small n.
Small n, yeah. Capital N should be huge. Again, I repeat, my comments, at least in the last 5 minutes, are valid only if Capital N is huge. You see, this will be the fluctuation, the relative fluctuation. If capital N is, let's say, 2, 1 over square root of 2 is something like 0.7. The relative fluctuation will be 70%. So, of course, you will observe fluctuations. But if N is the Avogadro's number, there's no way you will observe any fluctuation. Okay, finally, let's start with our statistical discussions. Let's start with a simple system, isolated system. Which means fixed energy fixed number of particles. And fixed volume. So E, N, and V, they're all fixed. This is what we call the macro state of the system. When I look at an isolated system, in the thermal or macroscopic isolated system, I don't see the individual atoms. I see the general behavior. Like I can determine the energy, the number of particles, the volume of the system. I don't really care about what each one of the atoms making my system is. Now, the state of individual particles this is what I call the microstate. So one is the macrostate, what thermodynamics is interested in. The other one, the microstate, the individual velocities and positions of the particles, or the quantum states of the individual particles, which we are trying to avoid calculating. Then the question is, that we will ask is, how many microstates correspond to given macrostate? Let's call this number omega. For a given system of energy, isolated system of energy E, number of particles, and volume V, let me just call this omega. Now, why are we interested in this one? Again, let me look at these two systems. System 1, system 2. One has energy E1, the other one has energy E2. Let me just assume N and V are fixed for both systems, so I will not write N and V as the arguments of omega. So let's say that the left-hand side has the number of microstates omega 1, the right-hand side has the number of microstates omega 2. Now, what is the total number? So the whole system has energy E1 plus E2. Now I can ask the question, what is the number of microstates of the whole system in terms of omega 1 and omega 2? If the first system has energy E1, it has microstates omega 1 E1. For each one of these microstates, the second system will have energy omega 2 E2. So if the left-hand side has energy E1, the right-hand side has energy E2, the total number of microstates corresponding to this specific macrostate, one having energy E1, the other one having energy E2, will be just a product. But now I'm also allowing them to exchange energy. So E1 is not fixed, E2 is not fixed, but the capital E is fixed. So if I look at the whole system, sum over all values of E1 and E2 such that E1 plus E2, which I call E, this should be fixed. So this is the total of microstates of my combined system. E1 is fluctuating, E2 is fluctuating, it can change. They are exchanging energy. But now I can ask you the question, what is the most probable value of E1?
We can try to maximize it.
Yeah. You see, the probability that the left system will have energy E1 will be given by omega 1 E1, omega 2 E minus E1 divided by omega E. You see, the numerator is the number of microstates in which the left-hand side has energy E1. The denominator is the total number of microstates. So the probability that the left-hand side will have energy E1 will be given by this ratio. And as your friend suggested, let's maximize this one. This should be equal to 0. Well, this is equal to 1 over omega E. Derivative of omega 1 with respect to E1, omega 2, plus omega 1 times derivative of omega 2 with respect to E2 times minus 1. Minus 1, this is E2. This is derivative of E2 with respect to E1. I'm just using the chain rule. This should be 0. Well, this tells me that derivative of omega 1 with respect to E1, omega 2 should be equal to derivative of omega 2 with respect to E2 multiplied with omega 1. Let me divide both sides by omega 1 and omega 2. So this tells me that 1 over omega 1 times derivative of omega 1 with respect to E2 should be equal to 1 over omega 2 derivative of omega 2 with respect to E2. Now this is E1. Or derivative of logarithm of omega 1 with respect to E1 should be equal to derivative of logarithm of E2 with respect to E2. This is the most probable, this condition will determine the most probable value of E1. Well, this should look familiar from thermodynamics. Del S1 by del E1 should be equal to del S2 by del E2. If when the system reaches equilibrium, that should be satisfied. You see, we only looked at the most probable state, but just, although I didn't prove it yet, remember all these earlier arguments. Look at this one. Look at this simple example. Although the probability that all my particles are on the left-hand side, or all of them are on the right-hand side, are not 0 for capital N finite, the probability is so small that I will never observe the system in that microstate. The macrostate will always, the microstate corresponding to my macrostate will almost always have half of my particles on the left and half of my particles on the right. And that system will not change. It will remain like that. You will not see all the particles by pure chance just accumulated on one side. It will not happen. The probability of this is 0 or negligible. So when I tell you what will be the microstate of my system, I can confidently say that, okay, half of them are on the left, half of them on the right. Well, the same thing over here. E1 can take any value from 0 to capital E. E2, again, can take any value from 0 to capital E as long as their sum is E. But for the most probable state, E1 and E2 will be such that this condition is satisfied. And the probability of observing any deviation from this condition will be negligible. So whenever I observe my system, my system will not change. It will always remain in this macro state. And that macro state is given by this equation. That is what we call the equilibrium. Things don't change. So this is the condition of equilibrium in statistical mechanics. Well, this is the same condition of equilibrium between these two systems in thermodynamics. They should give me the same condition. But that hints, at least, let's say, that S should be proportional to logarithm of omega. What is the proportionality constant? Well, again, let me just say that it is the Boltzmann constant. It can be, you can take it 1, but that will mean I will be looking at, I will be measuring temperatures in terms of energy units. But this is the relation between entropy and the number of microstates in statistics. You say, we already know one quantity, S. But if I know the entropy in terms of the other variables of my system, I can calculate all the rest. Okay, let's try to apply this. Let's see. Let's look at the ideal gas. Can I get some relationship just by knowing this much? I still don't know how to count the number of microstates. Okay, we are looking at classically, the problem classically. I'm counting the number of microstates. And, well, I can basically use this product rule. Or was it? Yeah, this one. The microstate basically is, if I state the position and momentum of all my particles, that specifies the microstate. So each different position of different an particle will give me a different microstate. I have my ideal gas within a volume V. Each one of my particles can be at any point along this line V, along this volume V. So I would expect my number of microstates to be proportional to V times V times V times V. How many of them? N of them. Well, I'm making a very simple assumption. I'm assuming that these particles making my ideal gas, that's the definition of the ideal gas, they are not interacting. If there is one particle at this point, the other particle can also be exactly at the same point. They can overlap. That's an assumption. Basically, I'm ignoring any volume that my particles making my ideal gas might have. Well, the density of states will be proportional to this n times some function that depends on the momentum. How the momentum is, in how many different ways we can distribute the momentum. But that will depend on the total energy. So the density of states somewhat should be now let me write the equality, some constant times V to the n times some function of energy. I don't know what this function is. Now, this is a crude guess. We will be more concrete when we are calculating these number of microstates. So I know omega, so I can write down S as Boltzmann constant times logarithm of omega, which will be Boltzmann constant times n times logarithm of v plus some terms that depend on the energy. Well, let's look at the differential of S. Remember the U, okay, U and E, they are the same thing. I will just use them exchangeably. More precisely, U is the average E for a given system, but if E is fixed, U, the average of E is also fixed. Even if the system exchanges energy with the environment, we will study such systems, the fluctuations will be negligible, so U will be equal to E even in those cases. So du was TdS minus PdV, or ds was equal to 1 over T du plus P over T dV. So in particular, the derivative of entropy with respect to volume at constant U is equal to P over T. Well, I know the volume dependence of entropy. I don't know how it depends on the energy yet, but I know the volume dependence. So I can take the derivative. ds over dv at constant energy is n times Boltzmann constant divided by v. So P over T is nkb over v, so PV is equal to nkt. So what did I do? You see, I looked at the statistics of my problem. I counted the microstates. I looked at the most probable state. Then I assumed that, okay, the most probable state is the state in which my system is in equilibrium. Then I saw this similarity between the result I obtained and the thermodynamic relationship I have for equilibrium, which allowed me to make a guess saying that S should be equal to the logarithm, proportional to the logarithm of the number of microstates. And then I just looked at the ideal gas. I just assume that I have a system in which the particles do not influence each other in any way. So if I am counting the number of microstates my system will have, each particle being at a different point will be a different microstate. Well, in fact, there are infinitely many points, so there is a question mark over there. But typically, I would expect the number of points within my volume to be proportional to V, the volume of my system, so the number of microstates of this n particle system should be proportional to V to the n. I just made some very simple assumptions. And this already, once I identified the relation between the entropy and the number of microstates, and for this very simple system, this very simple assumption, just in a few lines, led me to the ideal gas equation of state. So at least I know that I'm on the right track. Questions? Now, this identification, by the way, already tells me the third law of thermodynamics. Well, the number of microstates that my system will have at 0 temperature will be 0, will be 1. They are in the ground state. If omega is 1, logarithm of 1 is 0, so entropy is 0. So you see, although I can also satisfy this this equality for entropy is being equal to logarithm of omega plus some constant, but if I take that constant to be 0, I already have the third law of thermodynamics. Entropy at t equal to 0 is 0. Well, the third law of thermodynamics is more precisely the entropy of every system is equal to each other at t equal to 0. That constant can be chosen as 0. The second law is also here. How? Let's see. Again, let's go back to here. We know the condition of equilibrium. In equilibrium, this condition should be satisfied. But we didn't drive this condition requiring the equilibrium. We drive that condition by maximizing the probability. Suppose I have a system that is not in equilibrium. E1 and E2 does not satisfy this relationship. I bring them in contact. They will start exchanging energy. Then the most probable value of the energy will be given by this condition. But that condition is nothing but the maximization of the probability. Now, a given system will behave in the most probable way that it should behave. The increase of entropy is nothing but, it's just stating that a given physical system will evolve in the most probable way that it can evolve. It's just a law of probability. And again, can it violate it? Well, yes, it can violate it, but the probability of observing a violation of that law will be negligible. You won't be observing it. And the first law, well, that's basically energy conservation. You see here, by defining entropy in this way, you see the entropy in this way where omega will be a function of E, this says that I can express energy in terms of other thermodynamic variables. So since energy is conserved, I practically get the first law. Now there's still, for a night, here we have a very simple system. We don't know what this coefficient is, we don't know what this constant is. Let's try to be more specific on what do we mean by the number of microstates. Let's try to be more specific on this definition. Now, to do that, let's define the concept of the phase space. Well, this is something that you should be familiar with in analytical mechanics or classical mechanics. So you have 3 n particles. You have n particles. Each one of them will have the momentum p and coordinates q. So a phase space is a 3n plus 3n dimensional space of 6n coordinates and momentum. So the as an example, for example, let's look at the one-dimensional harmonic oscillator. So it has its momentum and coordinate. And if you tell me, if you specify a point in phase space, this corresponds to the specific momentum and coordinate of my oscillator, so that is the microstate of my system. So each microstate of my system corresponds to a point in phase space. The energy is fixed. But energy, in terms of the, I can write it as in terms of the microstate of the system. So this basically gives me a condition among the 6n coordinates in phase space, or specifies a hypersurface. If I go back to my one-dimensional harmonic oscillator case, if I know the energy of my system, then my system at any moment will be somewhere on this ellipse. My system cannot be at any point if I know the energy, if the energy is fixed, but it has to be somewhere on this ellipse. Well, similarly, if you go to 6n dimensional phase space, you will again have the surface that my system can be. And the number of microstates available to my system will be the number of points on this phase space. Now, the number of points is infinity, so it doesn't work exactly, but I can still make the assumption, let's say, is equal, let's say, proportional to the surface area of the hypersurface. Well, the proportionality constant over there, I mean, you cannot derive it from classical physics, but quantum mechanics tells us what that proportionality constant has to be. Because, okay, in classical physics, I can talk about points in phase space, and each point will correspond to a microstate. I can have two very nearby points in phase space, and still they will both of them will correspond to different microstates. I can distinguish them. But quantum mechanics tells me about the energy momentum uncertainty principle. So in quantum mechanics, the phase space, we cannot straightforwardly use the classical phase space, but if we still insist on using the classical phase space, quantum mechanics tells me that I can only localize microstates to some finite volume in phase space, using this delta x, delta p. This is the smallest that you can localize your microstate. Not a point, you cannot localize your microstates to a point, but to some finite volume in phase space. So that determines what this proportionality constant will be between the number of microstates and the surface area. Now, we will do some concrete examples where we explicitly calculate that proportionality constant. So for the time being, at least, let's just play with this idea of the number of microstates correspond to a given macrostate. That macrostate is specified by these quantities, is proportional to the surface area of the hyperspace in phase space allowed by my energy. Well, I'm also making an assumption here, by the way. For example, I can have, let's say, classically speaking, let's just look at the double well potential. And let's look at a system that has this energy. It cannot overcome that barrier. So initially, if your system starts on the left-hand side, it will always remain on the left-hand side. The microstates corresponding to the right-hand side should not be relevant to you. But we are assuming we will be taking all the surface area. So we will be saying that, it will be more clear later on. We will be basically assuming that all the microstates are on equal footing. This is an example where that is not true. But we will ignore those cases, and we will assume that my system can be in any one of the microstates that is consistent with the macrostate of my system. This is called the ergodic hypothesis. There are cases where this hypothesis does not work, or the ergodic assumption. But in most cases, in all the cases we will be dealing with in this course at least, it will work, it will be valid. So now our problem, how do we calculate the surface? Well, especially when we treat this ideal gas problem in quantum mechanics, it will again be more explicit. Usually it's not so easy to calculate the surface area, but easier to calculate the volume. Let me define this function gamma, which will be proportional. Well, the precise definition of this is number of microstates having energy less than or equal to E. Not equal to E, you see. Omega was the number of microstates having energy equal to E, but this is the number of microstates having energy less than or equal to E. And this will be proportional to the volume enclosed by the hypersurface in phase space. You see, if I again go back to this one-dimensional harmonic oscillator case, this is what I mean by the volume. The volume will be easier to approximate than the surface, the circumference. Well, then what is omega? Well, you see, we said that omega is the number of microstates having this definite energy E, but we cannot measure energy precisely. There will always be some error bars. So this will be equal to gamma, let's say E plus delta E over 2 minus gamma E minus delta E over 2. Delta E being the error bar in our energy measurements. Although we said that we are looking at isolated system, no system will be exactly isolated. There is always some interaction with the environment. So there will always be some uncertainty in the energy. So this is somewhat more precise. This will be the volume of a shell. Not the surface area, but the volume of a shell, which will be times delta E. Let me put approximately. So if I calculate gamma, I can obtain omega by taking the derivative with respect to gamma multiplying by delta E. Well, what is this delta E? Well, actually, I don't really care. You see, I am interested in the entropy. The entropy is logarithm of omega, which will be logarithm of del gamma by del E plus logarithm of delta E. Delta E will be proportional to n. The larger system, I will have a larger uncertainty in the measurement of the energy, but it will be of the order of n. But this del gamma by del E will be of the order of 10 to the power n. So this term over here is of the order of n, whereas this term is of the order of logarithm of n. This is 10 to the power 23. This is just 23. So I don't really care what delta E is. I can approximate entropy as logarithm of del gamma by del E. I'm not even writing approximate sign. So if I can calculate the volume, which you will see will be easier, then I know the entropy. Just take the derivative of the volume with respect to energy, take the logarithm, we are done. There's still this question of the proportionality constant. You see, this gamma I will calculate as the proportional to volume. I don't know the proportionality of volume. I need quantum mechanics to fix that proportionality constant. But I will calculate the volume, take the derivative of the volume with respect to energy, take the logarithm, and that will give me the entropy. Okay, before I forget to say, on Monday we have a lecture. Okay, any last questions? I will also upload sample questions the latest this weekend.
There is no exam on
this Monday, no. Next week, no.
For Wednesdays?
No.
No exam.
The short exams will be on Mondays. We will always have lectures on Wednesdays. On Mondays, next week, we will have a lecture. The following short exam, lecture, short exam. So see you on Monday.